Welcome to episode number 667 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by yours truly, Amelia Dalton. Folks, this week we are talking about autonomous systems, advanced machine intelligence, and how Palladyne AI is revolutionizing how robots and drones perceive and interact with the world. My guest is none other than Palladyne AI Chief Technology Officer and co-founder, Dr. Denis Garagić. Denis and I discuss the secrets behind their proprietary technology, their unique approach to AI challenges, and their vision for the future. So, without further ado, please welcome Denis to Fish Fry. Hi, Denis. How are you?
I'm great. How are you doing?
Good. All right. So, let's start off. Can you talk to me a bit about Palladyne AI's technology approach? And how are you guys different from a typical AI software powering robots and drones?
Sure. So our approach is really an approach to embody AI and physical AI. So we are not in the space of digital AI. Physical AI is really interpreted as AI that needs to interact with the world through the sensors that observe, but also act on the world through either robotic systems or through other means. So our principle is really using a closed loop autonomy approach. You observe, you learn, you reason, and you act, and all of that happens at the edge. We don't need to require huge amounts of data to learn how to act upon certain actions. We operate in dynamically changing environments in both cases of robotic manipulation as well as drones, and world will change dynamically. So we need to be able to learn how to act those changes. So that's the main distinction. So low data requirements, edge computing, all learning happens at the edge, and all inference happens at the edge.
So, Denis, talk to me about how Palladyne AI is different in your core technology versus other people in the field, particularly when it comes to efficiency, scalability, and domain specificity.
So the technology needs to be reliable and robust. You cannot operate industrial environment with accuracy or reliability of 80%. Nobody will talk to you if you say that my pick and place will be 80% reliable. Automotive industry, any industry requires even 99.9% accuracy and reliability. I believe with the current approaches that are very popular in digital AI and trying to be transferred into physical AI, which we collect huge amounts of data and try to basically train the robot to behave appropriately to those data, that's not achievable. If you look at any of the models that currently deploy as a foundational models, at best they report 92, 93% accuracy, which again, for some tasks is absolutely unacceptable. So our approach is really different because we don't want to rely on that data. That data for robotic systems is very, very niche data, very hard to collect and very proprietary to each customer. In our digital world, we are giving our data for free. You and me are giving data for free through emails, through interaction, internet. So therefore, that brute force of collecting huge amounts of data, archives of data, and then teaching models like LLMs or multimodal LLMs to spit out some inference is possible, but it requires still huge amounts of energy and time. Now, if you go back to robotics, so drone application, those are very specific to specific applications, very hard to collect, and there's no time to collect them in the quantity required for these huge models. So we cannot rely on that. So our approach is really, how do we actually find algorithmic approach that doesn't require huge amounts of data, is adaptive, and also responds kind of in probabilistic way. It doesn't give you huge amount of determinism, but you can narrow that determinism by additional tuning. So that way we can actually operate at the edge. We can teach the system at the edge, and proprietary data to a customer stays with them rather than being passed back to the cloud and turn huge amounts of computing to generate those models and push them back on the system. Reliability is a huge issue in industrial applications. Holding a line in any industry for less than an hour easily costs $2-3 million. That hold time or downtime is unacceptable to customers. So we need to provide level of reliability that we can guarantee. So our approach is more kind of, I would say, mathematically driven so that we can actually understand where we fail and how do we actually compensate for those failures. So if you have a current state-of-the-art foundational models that could easily have 30 billion parameters, who is going to tune those models and how to perform adequately? You can throw more data, but then collection data requires time and effort. So our approach is definitely less hungry on the data, adaptive, and changes the environment, and using really this principle of observe, learn, reason, and act that happens at edge at real in situ on a place. The way how we are scaling the computing in an LLMs, it's going kind of exponentially exploding. At the end of the day, we're going to have to have a nuclear reactor to feed those data centers. We cannot afford nuclear reactors for each robot to compute and learn using that type of approach. So we need to kind of figure out either fundamentally different approach to AI. Analogy, our brain uses only 20 watts of power to do all of that, which means that chemistry is probably most efficient way of computing, but we are not capturing that in current models. So I can address this later because we can discuss some of the aspects of the future. Where we're going.
Sure. Okay. So, first, walk me through a specific example of a challenging AI implementation that you guys successfully executed.
So there's a few applications. So we have two products. One is called Palladyne AI, which is specifically designed for robotic manipulation in complex environments and complex tasks. It can be actually transferred to any number of tasks rather than just being point solution. And the second one is a collaborative swarming application for mobile machines, so drones in this case. So I'm going to give you an example, probably a bullet, but let's focus first on the robotic manipulation. So we have a successful implementation in maintenance and repair industry, especially aerospace. The planes need to be repaired every certain number of years. They have to be stripped of the paint. They have to be decommissioned and put together. And that operation is highly manual, but also stripping the paint, cleaning, sanding, it's also highly manual. And current kind of automation type of a solution requires each part to be well known to the user and apply traditional automation approach, apply trajectory over that. But what if you get like 100 parts, and for those 100 parts, you don't have specific CAD models, and you want to load your chamber that does, for example, stripping of the paint or stripping of the substrate and do increased productivity. So that's not possible. So we actually jump into the situation in which customer deployed more than 4 robots that in a very specialized chambers that haven't been used for 7-8 years because they couldn't use the software without very highly engineering skilled workers. So our low-code, no-code autonomy IQ software was able to turn technician into really controls a robotics engineer within 2 hours of training. And without additional understanding of perception or motion planning or tasking, the user was intuitively able to program the robot to increase productivity by loading the chamber with as many as possible parts. And then our system would actually recognize how to avoid each part, how to avoid a constraint in the space, how to dynamically avoid singularity of robotic systems in which robot gets locked. So it was increasing efficiency, but most importantly, technician and line worker was turned into this controls engineer without any additional support from engineering. So now you have a basically technician serving that role in which engineering resources are scarce and expensive, but productivity can be increased with this line worker force through our software. So that's one example. And then also on the kind of drone side, when we use collaborative autonomy, we are using multiple drones to increase productivity or efficiency. Public safety domain is a very critical application. If accidents happen on the highway, the easiest way to reach that point is to first respond as drones so they can be dispatched. If you dispatch multiple drones, you have a higher chance of understanding what's happening in overall scene. And when they collaborate in sort of decentralized way, they are able to provide a situational awareness to a single point or central location without providing that information to each individual user who will operate drones. So now suddenly we have a human on the loop orchestrating multiple drones and then queuing the other emergency services how to approach that disaster or an accident location in most optimal way so that it can save the lives. So those are kind of two applications that we've been covering. Commercial space. We can cover some of the defense applications, but those are kind of extendable to other domains.
So, given the rapidly evolving AI landscape, what is Palladyne AI's long-term strategy going forward?
So we believe that our system needs to be extendable across domains, across platforms, and across tasks, across sensors. And that's how we're designing our system, because if the system is only designed for single point solution, obviously it's not scalable, because how many of those use cases are going to have? And we designed the system to be actually extendable to different platforms. And we call it, for IQ, we call it is really hardware agnostic. We are covering most brand names in robotic manufacturing, from Panoke ABBs and URs and Kawasaki's and all the robots, as also end effectors. So it's basically, as long as that sort of configuration exists, it's plug and play. So you can repurpose already existing robotic systems without investing additional money. So you're enabling existing robot to become more intelligent or more purposeful for different tasks. Traditional automation, you have a body shop, body floor of the robots, and they're only programmed for one task. So with our software, you can actually easily repurpose that robot for different tasks without spending additional 6 months of pre-programming or reprogramming those robots. So that's one aspect. And then we apply that also to the drone part. It's agnostic to the drones, agnostic to the type of sensors. Multimodality is critical. Perception usually is associated only with computer vision, but our perception understanding is all sensors that we can sense, from acoustic to touch to force moment to obviously computer vision. But all of those sensing modalities, when they're combined, enable you to actually perceive the world much more accurately and then apply those actions more accurately. So that's kind of moving in that direction of kind of cross-domain, cross-platform, and cross-task solution.
So, Dennis, how does Palladyne AI approach ethical considerations of deploying its AI technology? And what kind of specific safeguards or frameworks are in place to ensure responsible use?
So like any machine obviously has the constraints. So and those constraints in many cases are even more rigid because they want to contain into the kind of workspace of the, for example, robot. So we operate within those constraints. We don't allow AI to exceed those. So everything is operational within the constraints of robot, which are also safety imposed regulations. And then within that space, you also optimize to maximize energy, to again maximize safety of humans within that reach. We always use human on the loop as the sort of final decision maker of either applying the actions or letting robot to complete the action. So those are kind of our main safeguards, the human on the loop, and then following or including the safety constraints that come either from the industry regulations or from the specific customer. And so those are kind of embedded, or customer can actually configure those constraints to guarantee that actual solution that AI will provide is safe and optimal for the execution of tasks.
So, beyond current applications, what emerging or blue sky areas of AI research are you guys the most excited about? And how do you anticipate these will shape the future of business operations?
I'm smiling, but my future is that I want to change completely trend of current AI because it's not sustainable and not efficient. It works for companies making GPUs. They're fantastic because they keep making more of those. But again, my analogy with the human really computation is 20 watts of power for all of our processes. And it's an amazing machine, which means that we don't have a right compute mechanism for the current AI. So my dream, which we actually worked almost 10 years ago now, actually my research before, is to really understand how chemistry computes. And because chemistry is most efficient way of computing, if you can figure out this thing, our models will be power efficient. Our models will be able to receive multimodal data, process them in a sort of extensible way to any number of tasks. Now, we are not there, but I also don't like to jump on these kind of hot topic trends and then we go into the corner in which we cannot move anymore. It used to be desirable computing is kind of polynomial scale. But now we are moving really in exponential scale. We just keep throwing more and more computing. And I don't think we are getting the results for that expense. That's kind of like, futuristic way. But really, in a reality, the key for us is really to understand how do we combine multimodal sensor fusion upfront, because that's a critical way to understand what is the critical information that we need to collect. Rather than collecting everything, focus on something meaningful. And that's only extractable by combining sensing modality as we do. Like, I can close my eyes, but if I hear your voice, I can reconstruct your face because I already saw you once. I don't need to be staring at you all the time. So utilizing that multimodalities and sensing technology is improving dramatically. But on top of that, how do we actually control those sensors to really tune into that information that you need for a specific task? So if you're doing robotic manipulation, you don't need to know everything about the world around you. You need to really focus on what matters. Our approach to AI allows us to kind of create what we call success-based learning, which means like reduce number of trial and error exploration, but use what humans already understand, what's well done, and really focus on your exploitation task. And that way you create efficient models that can be learned with a few demonstrations or few exemplars and use them as a sort of your vocabulary or action space. And then combining those comes through a sort of reasoning engine that doesn't have to be, again, deep learning. It could be probabilistic. It could be something that stitches those kind of actions based on what we perceive them. So we are moving in that kind of direction. Again, ideally, I want to step away completely, but trend is currently in this deep learning through more computing. But at the end of the day, if you want to compute at the edge, you don't have that device that currently can host these huge models. And that's what's kind of struggling in industry. Again, 30 billion parameters model is very hard to understand why it's failing and how to actually correct what they fail, unless you collect more data and retrain those things.
Sure, that absolutely makes sense. Now, Dennis, for organizations just beginning to explore AI integration, what do you think are the three most critical pieces of advice or first steps you would recommend?
Well, one is don't jump on the latest shiny tool because it may not be right for your application. Really think, is it right for me? Is it right for my application? Second one, don't really jump again on the open source that's associated with that shiny tool, because to productize software to really deliver to industry, you will spend more time, as might as well start from scratch. I don't want to say like doing everything from scratch because you don't want to reinvent the world, but really pay attention. Do you actually understand the cost associated in making those open source code functional within that sort of restriction and high standards of industry? Reliability is the key. Speed and compute speed of all this stuff. And then really be open-minded to look maybe even in older techniques that maybe run out of fashion, but maybe they ran out of fashion because at that time computing power was sufficient. So, just be open-minded. As AI is a big world, we knew about AI since 50s. In different forms and shapes, they kind of, waves. So AI came and they reinvented themselves. So I don't believe that what we currently have should be just called AI. There are many approaches to that. So just be open to that.
I love it. All right, Dennis, before I let you go, it's time for your off the cuff. So, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
Well, I don't need a passport to get there because I'm a very good cook, so I can make a meal from any part of the world. But since it's kind of cold here and I love French food, my favorite is a beef bourguignon. And it's simple, but if you use good ingredients, it will be fantastic. And I mean, it's a middle day here. It's not good for wine glass, but if you're in France, you will get a glass of wine too.
Yes, it is too early for a glass of wine here, but I would take that in a second. Well, Dennis, this was super cool. Thank you so much for joining me.
Thank you, Amelia.
If you'd like even more information about Palladyne AI, I've posted a couple links below the player on this week's fish frying page on eejournal.com and in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If LinkedIn is more your thing, I dig it. You can follow us or me on LinkedIn, and we are also on Blue Sky Social and Mastodon too. And we have that YouTube channel I just mentioned, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me, and our animated series called Libby's Lab. And of course, you can subscribe to our EE Journal YouTube channel as well. Thank you, everyone, for tuning in. If you know of any cool new technology or heck, you just want to chat, shoot me a line at Amelia, that's Amelia, at eejournal.com, or post a comment on our forums on EE Journal. For the week of January 30th, 2026, I'm Amelia Dalton, and you've been fried.